Okay, welcome everybody. This week we have Selvi from University of South Alabama, and she's going to talk about monomial ideals of graphs and their syzygies. We also know Selvi from the Meet a Mathematician project. Maybe she wants to start with saying a couple of things about this project and then tell us about some commutative algebra.
Okay, great. Well, thank you to the organizers for putting together this great seminar series and also inviting me to give a talk as part of this. Well, Meet a Mathematician is a video collection of short interviews with mathematicians from underrepresented backgrounds. In the US, there is a big representation problem, and we try to address this problem by highlighting the profiles of mathematicians from many diverse groups. So we have a website, we have a YouTube channel, we keep interviewing people. The number of interviews we have is increasing, and people share their personal stories of how they get started in math, what kind of struggles they had, their accomplishments, and they share some words of wisdom at the end of their interview. So it could be a good resource for you and for your students. And if you'd like to learn more about the project, please write to me, or we can talk after this seminar. Okay, so today I'm going to talk about monomial ideals and these ideals associated to graphs and their syzygies. So first we will start with what a syzygy is, and then through that I will start describing what a minimal free resolution is, because syzygies appear in minimal free resolutions. But then I'll introduce my main objects that I will work with in this talk. These are called edge ideals of weighted oriented graphs. And after a little bit of discussion on where they appear, what kind of difficulties come with those objects, I will talk about some of the results I have from these two joint works. The first one is a joint work with Biermann, O'Keefe, and Lin. And the second part is a joint work with Casiday. She was a high school student when we started this project, and now she's an undergrad at Yale. So she did a great job. Okay, so let's set up our notation. Throughout this talk, K will denote a field, and we don't specify what the characteristics should be, and our results are characteristic free. And we're going to work with standard graded polynomial rings. So standard here means degrees of variables are 1. And graded means polynomial rings come with a graded structure, right? So you can talk about degree 0 pieces, degree 1 pieces, and so on. And then all the modules that we're going to work with are graded, or if we're talking about ideals, they're going to be homogeneous ideals. And the notion of gradedness comes very naturally when you talk about varieties in the projective space, right? So this is a very natural notion. Okay, so I'm going to work with homogeneous ideals or their quotient rings. Sometimes I will prefer the quotient ring over the ideal because minimal free resolutions of quotient rings are longer. So I'm trying to get as much as I can get out of that resolution. So the first result I want to recall is Hilbert's basis theorem. So when we're in a polynomial ring, it is Noetherian, right? So every ideal is finitely generated. So the question I have here is, okay, if I know an ideal is generated by finitely many elements, do I know everything about the structure of that ideal? Or you can generalize this question to a module over your polynomial ring, or in general, any finitely generated module, okay? So how do we describe the structure of a module? Knowing the generators is enough? Like, do they tell us everything we need to know about the structure? So in this example, we have a very simple ideal, which is generated by x, y, and xz in the polynomial ring over 3 variables. So when we look at these generators, okay, there are 2 of them, but they can interact with each other. We can look at the relations between them, right? So there's this natural relation between x, y, and xz. When you multiply the first one with z, second one with y, negative y, and add them, you get a 0. So this is a non-trivial relation between the generators, right? So besides the generators, the form of those generators, we are interested in understanding the relations between generators. If we want to fully understand the structure of the module, right? This is a very natural thing to do. So then among the relations between the generators, there may be relations. So if you keep doing this, you kind of resolve the ideal, and this kind of gives you an idea on the structure of your module, right? So which brings us to the free resolution. So Hilbert's approach to understand the structure of a module was through free resolutions. Every module has a free resolution, right? So this is like this complex going towards the left, and each step you have these free modules. But actually what you do is you're resolving your ideal or module, right? So in the first step, this comes very naturally. You know the generators of your module. So this map is given with the generators. But then if you look at the kernel of this map, you have your relations on the generators, and we call them syzygies. But because you can keep looking for relations of relations, so you have first syzygies, you have second syzygies, you can have third syzygies. And one question you might ask at this point is, well, does this go to infinity or does it terminate at some point? So Hilbert's syzygy theorem tells us if you're working with the polynomial ring, it will eventually stop, and the length is at most the number of variables in your polynomial ring. So this is a very powerful result. Okay, so let's look at this example. We were working with this ideal generated by xy and xc, right? And we've seen this one relation among the generators, right? So I said the first map is given with the generators of your ideal. So we multiply whatever we take from here, we will multiply with xy and xc and add them, and it will stay inside the ideal, right? So when you look at the kernel of this one, you're actually looking at the relations between these two. And if you remember, we found those coefficients z and negative y. So they give one generator for the relations among the generators. Because you have just one relation, this terminates because there's no relation to look for when you have one generator, right? So this terminates. So here I said minimal free resolution, right? I talked about free resolutions, but now I'm talking about minimal free resolutions. So where does the minimality come from? So when we're looking at these relations, if you pick the minimal relations, you will have minimal free resolutions, right? But the minimal free resolution makes sense in two cases, in the local case and the graded case. So local case is when your ring is a local ring. Graded case is when you have a standard graded polynomial ring. Okay. So we can do better than minimal free resolutions, and we can actually keep track of the syzygies, or all these things that we use in the relations, right? So because these generators are in degree 2, I can shift my free modules by the degrees of these generators I see here. So if you remember, the relation we found for the generators of the ideal was in degree 3, right? So that is why you see this degree 3 shift. So minimal graded free resolutions keep track of these relations of relations, but by also paying attention to degrees of each syzygies at each step, right? So we encode a lot of information about the structure of the module here. So in general, minimal graded free resolution is an exact complex of this form. So what I write here terminates because we're in the polynomial ring. And the only thing I change here is the form of our free modules that appear at each step of our free resolution, right? So what I know here is these will be copies of shifted R's, right? So at the 0 step, we can look at the number of degree J pieces, and we will record it with beta 0J. And you can keep doing this at each step, and at the last step, you see we have these like step showing up in the first component of these numbers here. So minimal free resolutions are unique up to isomorphism. That is why we say the here, because they are unique. We can talk about invariants of modules or ideals, right? So okay, then Betti numbers are the first things that we look at. So Betti numbers are these numbers that show the degrees of syzygies at each step, right? So when we look at beta ij, we call it the ijth Betti number. I tells us the step that we are in. J tells us which degree syzygy we're looking at. Okay, so you can put together all the Betti numbers in this thing called Betti table, right? So what we see here is this horizontal row will be denoted by I, so it's the first component. And these vertical rows will denote the j, but in this case, I'm going to write my beta number as beta I plus j. So when you're looking at the ith column and the jth row, you actually have the beta number, I plus jth beta number. Okay. So it's really hard to find the beta numbers in general, and like beta numbers carry all the information related to your minimal Fourier solution, right? Because it tells how many things will appear at each steps with which degree shifts. So because it's hard to find beta numbers, you can focus on coarser invariants like projective dimension and regularity. So projective dimension is given with this definition, but you can think of it as the length of your minimal Fourier solution. And in the Betti diagram, it's going to be this last number you see in that horizontal row. So regularity can be considered as the width of your minimal Fourier solution. And in the Betti table, it's going to be the last number you see in that vertical row, vertical column. Okay. So, but again, these are coarser invariants, but hard to find in general. Like classification is a big problem. We don't even know classification of all the ideals whose regularity is equal to 3, even for specific cases. So we can describe coarser things, but we don't know like classes where you know the values for those coarser invariants. Okay, so in an attempt to refine these coarser invariants, extremal Betti numbers were introduced. So extremal Betti numbers are read from the Betti tables. So these are the upper left corners of block of zeros. Let's say I have a 1 here, and everything below and to the right are 0. So this number here is going to be like these two will be extremal Betti numbers because this is on the upper left corner of a block of zeros, and this is on the upper left corner of a block of zeros as well. Okay, so these are the kind of things that I want to look for. So, but in general, like I said, it is really hard to find general formulas for Betti numbers of any homogeneous ideal, and even for the coarser invariants. So what are the, like maybe we should change our question, and instead of asking for like what is the minimal Fourier solution, maybe we should ask, well, can we establish bounds for large classes of ideals? Maybe not for everything, but for some. Or like, can you talk about like very tight bounds for special classes, or can you do better and compute those coarser invariants? Or the part that I like the most is, can you find combinatorial connections? Okay, so which brings me to my main ideal. So we're going to focus on monomial ideals. And this is still a very mysterious field. We still don't have a complete picture for monomial ideals. That's why we associate monomial ideals to like combinatorial objects like graphs, weighted oriented graphs, simplicial complexes. Okay, so my objects are weighted oriented graphs, and I'm interested in their edge ideals. So what is a weighted oriented graph? Well, we're going to, it's like a regular graph, you know, with vertices and edges, but we have a weight function. So for each vertex, I'm going to assign a weight. And then there will be an orientation. So when I talk about the edge set of an oriented graph, I have this notation to say my edge is oriented from I to J. Okay. So in this example here, let's we set up our weights for each vertex as the index of the weight. But you could assign anything really, right? So this is just some function that you define on your vertex set, but you want the values to be positive. Okay, so let's say weight of x1 is 1, weight of x2 is 2, weight of x3 is 3, weight of x4 is 4. And the orientation is given in this way, okay? And on this graph, I could talk about many different orientations, right? This is not, like this is just one of them. But for this given weighted oriented graph, my edge set would be x1, x2, x1, x3, x3, x2 to show the orientation from 3 to 2, x3, x4. So one thing I want to mention here is this vertex x1, everything is going away from x1, right? So this x1 has a special name and it's called source because everything is going away from it. And this other vertex, x2, it's receiving everything, right? So it is the sink vertex. So when you have source vertices, they're not going to contribute to our edge ideals so much, and we will see that in the next slide when we define what an edge ideal is. So edge ideals are related to they come from the edges of your weighted oriented graph, but they depict two things. It shows what the orientation is, and it also takes into account the weight of the target vertex, okay? So this is the same graph we had in the previous example. So for this one, if I were to write the edge ideal, so for this edge from x1 to x2, I would have x1, x2 square. Because x2 is target, I'm going to just record the weight of that one in the exponent of x2. So we have x1, x3, so the generator corresponding to that edge is x1, x3 cubed, and so on, okay? And because source vertices, like this was a source vertex, right? You never see them as a target, so their weights, even if you assign 100 as a weight to a source vertex, you don't really work with it in the algebra side. So because of that, whenever you have a source vertex, we will assume that its weight is 1. Okay. So why do we work with edge ideals of weighted oriented graphs? That can be one question. So there is a very extensive literature about edge ideals of graphs. So when the weights of all the vertices is 1, orientation is not really recorded there, right? Like you get rid of the weights, you get rid of the orientation, and what you have as the edge ideal is edge ideal of the underlying graph without the orientation and the weight assignments, right? So edge ideals are these like objects that are really well studied, but still we don't have a complete picture for those classes of ideals. So you can think of edge ideals of weighted oriented graphs as generalization of edge ideals in general. But that's not the only reason. So one of the appearances of edge ideals was in the field of algebraic coding theory. And this ideal was the ideal that showed up. So if you look at this, this looks like edge ideal of some weighted oriented graph, but let's look at what kind of structure it has. So we have xi, xj to the wj. So orientation is given with I to j. So you're taking all the vertices, connecting one vertex to all the other vertices in the graph. So you have a complete graph actually, right? So complete graph is, so let's talk about complete graph on 4 vertices. So let's say x1, x2, x3, x4. So, but the orientation is given from small vertex towards the larger index vertex. So we have x1 to x2, x2 to x3, x3 to x4. So everything is pointed in this direction, and you have a special condition on the weight. So you want them to increase and have length greater than 2 at each one. Okay, so this ideal appears as the initial ideal of some vanishing ideal actually. When you define a projective nested Cartesian code, you use a projective nested Cartesian set and you evaluate it under a degree D evaluation map. So when you look at the images, you create your projective nested Cartesian codes actually. So when you look at the initial ideal of that vanishing ideal on the Cartesian set, the initial ideal with respect to lexicographic order is actually that edge ideal. It's a very special example, but it appeared there. So it was a motivation for us to pick up on these objects. So these degrees of the evaluation maps which determines the projective nested Cartesian codes carry a lot of information about the minimum distance. Minimum distance is it's an important question to find the minimum distance of a code, right? So that degree D tells you when the optimal degree can be achieved, and regularity is a strict upper bound for that optimal degree. So that's another motivation to look for these algebraic invariants we introduced. Okay. So the next question you might ask, okay, so if they appeared and if they're considered as a generalization of edge ideals, what is known? Are they well-studied objects? They're not really well-studied objects, and actually they are very new to the field of combinatorial commutative algebra. So there are two groups. So one group studies the Cohen-Macauliness, and in the last 3 years, there were these papers studying the Cohen-Macaulay feature of the edge ideal of your of our weighted oriented graphs. And for the regularity and projective dimension, there was not much known at the time. And the first result that is out there when we started working on this one was just considering cycles and paths, but with a very specific orientation and a weight assumption. So everything was naturally oriented, like everything is in the same direction. And you want each vertex to have non-trivial weight, meaning your weights are greater than 1. Okay? But nothing is really known about the Betti numbers. And that is going to be the direction I will follow in the second part of the talk. Okay, so what kind of difficulties come with working with edge ideals of weighted oriented graphs? They are not square free. The only time they will be square free is when your weights are 1, but in that case, you recover edge ideal of a graph, right? And there is already a literature about that, so maybe your question is answered in that case. So we're not going to work with the square free version. And if our edge ideals of weighted oriented graphs are not square free, well, we don't have the toolbox that was there for square free monomial ideals. So the toolbox I'm talking about is the Stanley-Reisner correspondence, which allows you to study the Betti numbers of a square free monomial ideal by using Hochster's formula. You can go to the Simplicial complex and look at the holes of that Simplicial complex to read of the Betti numbers of a monomial ideal. This is a beautiful connection. So this is the first difficulty. We're not square free and we don't have a square free toolbox at our service. The second difficulty is these edge ideals, generators carry so much data, right? What kind of data we're talking about? Orientation and the weights, right? So if you have different weight assignments, it changes the ideal. If you have different orientation, it changes the ideal, right? So this makes it very difficult to provide general formulas for algebraic invariance. Okay? So maybe I'll give a little pause here and see if there are any questions, if I'm going too fast or slow, or this is okay.
No questions from me.
Okay. Okay, then. So I think right now, hopefully everyone sees what kind of objects we're working with, how they're defined, and if you're familiar with the edge ideal theory, you see hopefully you see the points I was trying to make in terms of like why these are difficult compared to edge ideals. Okay, so I said we don't have the Hochster's formula. That comes from the Stanley-Reisner correspondence, but we will have something nice to replace it with. So I'm going to introduce two tools here, which are not the only ones, but these are the ones that I'm going to mention in today's talk. So the first one is like a Hochster-like formula. So Hochster's formula, I said, whenever you have a square-free monomial ideal, you have a simplicial complex associated to it, right? So you can talk about chain complexes of simplicial complexes and then read the Betti numbers of that. But you can talk about Betti numbers of Stanley-Reisner ideal, right? You do algebra. So that is a beautiful connection to read one algebraic thing from the topological object you have here. But in this case, when we're working with a monomial ideal, not necessarily square free, we don't have that simplicial complex correspondence, right? Like you don't have one simplicial complex that is in one-to-one correspondence with your monomial ideal. Maybe you could polarize your ideal and get a square-free monomial ideal and then talk about the simplicial complex, but that's not what we're going to do. So in this case, when we are working with the monomial ideal, instead of Betti numbers, we're going to have this formula for multi-graded Betti numbers. So there was this grading I've talked about, right? N grading, natural grading. We were talking about degree 0, degree 1, degree 2, and higher degree pieces, right? But you could also talk about each piece, like what do you see in the first component? What do you see in the second component? So you could actually refine that grading and talk about a multi-grading. Right? So multi-graded Betti numbers are associated to these n vectors from n to the n. Right? So you have these n tuples. And then when you look at the Betti number at the I step with the multi-graded degree B, you can express it in terms of dimensions of reduced homologies of this object called upper causal simplicial complex. Okay, so the definition of upper causal simplicial complex depends on the ideal and this multi-degree, and we will see the definition here. Okay, so this is really nice because I have this algebraic thing on the left-hand side, and on the right-hand side, I'm talking about wholes of some simplicial complex, right? Okay, so how do we define the upper causal simplicial complex? We fix our ideal and we fix our multi-degree. And then you want to understand what kind of things can be faces in the simplicial complex. And the way you determine it is by looking at this ratio. So we fix our multi-degree, right? So you're at this lattice, like at the point B in that lattice, and you're looking at directions you can go from that point and see in which direction if you go, you still stay inside your ideal, right? So this ratio can be expressed that way, right? You're at a point, which direction you want to go to stay inside the lattice that corresponds to your monomial ideal I, okay? So for each of this x to the f here is the notation that says for each of the vertices that is inside your face, you're going to use the variable xi. So I abuse the notation here and use the vertices as the variables of our polynomial ring and so on. Okay, so let's do this one example. So our ideal is the edge ideal of a cycle. So this cycle is oriented in the nice way. So we're going through the clockwise direction. Okay, so the way I assign the weights to each vertex is I will just say everything has weight 2, right? So that's what you see in those coefficients. So I go from x1 to x2, weight of 2 is 2. I go from x2 to x3, weight of 3 is 2, x3 to x4, x4 to x1. Okay, so that's our orientation, and our weight assignment is 2 for each vertex. If I want to talk about its upper causal simplicial complex, I need to specify a multi-degree. Right, so let's say the multi-degree we choose is given with 2 at each component. Okay, so I'm interested in describing the simplicial complex, upper simplicial complex for this ideal at the multi-degree B. So what I claim here is, so this will be a simplicial complex on 4 vertices, right? Because variables of your vertices of your ideal will be vertices of your simplicial complex. So what I claim here is x1, x2, x3, x4 is the only minimal non-face of this upper causal simplicial complex. Okay, so you can prove it by using the definition of upper causal simplicial complex, right? So the condition to be a face in the simplicial complex was if you divide x to the b with x to the f, does it stay inside the ideal or not? When I say x to the b, I'm associating it with the monomial, which has the components of your multi-degree at the corresponding variable, right? So you have x1 square, x2 square, x3 square, x4 square. For xf, you're talking about multiplication of monomials, vertices that are inside f. So you have x1, x2, x3, x4. So when you divide them, what you have is x1, x2, x3, x4. It does not live inside this ideal, right? For something to be inside that ideal, you need to have degree exponent 2 for at least one of the vertices, right? Okay, so it's not in there, but if I want to show it is a minimal non-face, none of the proper faces of this one should be contained. If it is a minimal non-face, all the proper faces should be inside our simplicial complex, right? So, okay. Then I'm going to take away one vertex at a time from F, and you can check this if you look at, if you take out one of these, you will have something inside the ideal. If you take away x3, it will stay inside the ideal. If you take out x2, it will stay inside the ideal. So what you see here is, this is indeed a minimal non-phase. But what kind of a simplicial complex does this correspond to? You have an empty tetrahedron, right? Okay, so for this ideal, we show that it's, the simplicial complex will have non-zero homology at the non-zero second homology, right? Because you have a hole in dimension 3, right? So you will have all the faces of it, but without the 3 simplex there, 4 simplex. Okay, so because you have just dimension of this homology, reduced homology is 1, so from that theorem we had Huxley-like formula, so beta 3b is 1 for the edge ideal of our cycle, right? And you can push it one step further and associate it with the minimal Fourier resolution of R mod I. So what you do is, in the minimal Fourier resolution, you would just augment this surjective map to the right-hand side, and you would just increase the length of your minimal Fourier resolution by 1 if you're working with the quotient ring. Okay, so the projective dimension of this ideal is actually 4. This is the maximum length it could achieve, really, right? Based on Hilbert's Syzygies theorem. Okay, so I'm taking so much time explaining my tools, so hopefully I will have time to talk about my results too. Maybe I won't cover everything, but at least the first part. Okay, so the second tool we have is called Betti splitting. I'm not going to get into details of it, but the idea is, if you have a big ideal and if you want to understand its Betti numbers, maybe you could look at smaller ideals associated to the big one and describe its Betti numbers in terms of the smaller ones. So if you have an ideal I, whose generating set is given as a disjoint union of the generating set of J and K, and if you have this kind of an expression for the Betti numbers of your bigger ideal, you call this sum a Betti splitting, because you can read off the Betti numbers of your big ideal in terms of the smaller ones and how they interact with each other. So this is my second tool. Okay, so I can start talking about my the first results.
Selvi, previous theorem, what is the theorem?
So this one?
Yes, what is the theorem here?
Actually, this is the definition, so that's a typo.
Thank you.
That is a typo. So it's the definition, what a Betti splitting is. There was a way to describe a Betti splitting, so it's hard to find what constitutes a Betti splitting, hard to detect them. So there was one theorem that I was going to include, but then I decided not to. So this is a typo, and thank you for pointing that out.
Thank you.
Okay. So in this first part, I feel like this is going to be the only part that I can cover in today's talk. So the focus of the our objects in this part are paths and cycles, okay? And we're going to fix our orientation, and our orientation will be natural orientation. So what do I mean by natural orientation? If you have a path, so path is what you expect, right? So this is an example of a path. So you have, let's say, x1, x2, x3, x4, x5. So you just join each of these successive vertices and you create a path. So we say these are naturally oriented if every edge is oriented in the same direction. Okay? So we say a cycle is naturally oriented if it is oriented in the clockwise direction or counterclockwise direction. So let's say this is how it will look like, okay, for a 4 cycle. And for the sake of simplicity, I'm going to use these notations to talk about regularity, projective dimension, Betti numbers of the quotient ring. So all the results I will have will be given for the quotient ring. Okay. So let's recall the unweighted, unoriented case from the edge ideal theory. So if you have an undirected path on n vertices or an undirected, unweighted cycle on n vertices, you can compute its regularity in terms of the number of vertices you have on your path or cycle, and it is given with the floor of this ratio. So in this example, you see a path on 8 vertices and its regularity is equal to 3. So what happens if we assign an orientation and a weight? So how does the regularity change for this path? So in this case, what you see is we have the natural orientation, because that's the orientation I fixed for the first part of the talk, the results part. And our weight is 3 here. So what you see is regularity increases, right? Okay, so let's see what happens if we change the position of this weight. So it goes down. The reason we have these examples is to show that if you change the position, you see that regularity changes. So positions of non-trivial weights play a role in describing the regularity, right? Actually, so more than the weight, and so weight plays a role and its position too, and we have this formula for paths with one non-trivial weight. So let's say you have a non-trivial weight at vertex xp. It can be anything except the first one, right? So we're on a path, we have a non-trivial weight at the second or any other vertex. And let's say that weight is denoted by W. So you can describe the regularity of the edge ideal by looking at this sum. So what does this sum tell us? The weight appears in the regularity, but more than that, you care about the position of that non-trivial weight. So if you look at this part here, n minus p, n was the length. So when you're looking at this path, okay, and let's say you're at this vertex. So you care about this distance, like your distance from your vertex to the last vertex. So it's recorded here. You also care about this distance, and you see that contribution here, right? Okay, so generalizing this, like how will we generalize this? And we will see a couple of examples. So let's start with this path in the middle. In this middle path, what you see is we have more than one non-trivial weight, right? So we have a non-trivial weight at 2, 4, and 3. Okay, so regularity of this path is equal to 10. So I'm moving away from this path to 2 other ones. They look very similar, but what I change in the first one is you have the same weight positions. So if you compare these two, all the non-trivial weights appear at the same positions, right? The only thing I change is I swap these two, right? So if you have the same weight values but shuffled around, you have a change in the regularity, right? So even if you know the positions, you have to pay attention to which weight appears at which vertex. So let's look at this other path. In this one, we have the same weight values. So we have 4, 2, 3, 3, 4, 2, 3, 3. But what we change here is, instead of having 3 here, we moved up to the next vertex, right? So this time you see the same weights, but you change the positions. So what happens is regularity dropped down, but more than how it dropped down in here. So what's going on, right? Like if you change the weight positions or the weight assignment, there is a change in the regularity. And so we want to understand how this changes, and we want to come up with a formula to explain this. Okay, so in order to describe this, we introduce this thing called weight sequence. So from the examples we saw, positions of non-trivial weights was important. Like we need to record it somehow. So on our weighted naturally oriented path, so let's say P1, P2, Pk are the positions of non-trivial weights. What this means is like, oh, you have something at second vertex, you have something at fourth vertex, and you put together all those positions and create this weight sequence. And our suspicion is the positions and the weights and the distance between those successive weights will play a role in regularity. So that's why we introduced this thing called weight position sum. So weight position sum takes into account sum of all the weights and the difference between successive weights in this sequence, okay? So, but when I describe weight position sum, I describe it for subsequences of my weight sequence. So what do I mean by that? I have a weight sequence, which is the positions of all non-trivial weights, but I'm going to pick pieces, like I'm going to look at smaller pieces of it, but I'll keep the same order, right? If I have 2, 4, 5, I can choose 2, 4 or 2, 5. We will see an example of this. But for each of these subsequences, you can talk about weight position sum. This is something we introduced in the paper. And it tells you something in terms of the weights and the distance between each of these weights in your subsequence. Okay, so let's see why this is something interesting, or like how we came up with this weight position sum. So if you remember the formula for a path which had one non-trivial weight, so we had its weight, its difference, the distance between the vertex and the last vertex, and this about the position, and then you subtracted 1. So in our weight position sum, we take the sum of all the weights for the vertices coming from your subsequences, and because we have t many vertices that we take into account, we take away t. So in a way, this is an attempt to generalize the formula, okay? So next part, so we describe actually what the regularity of a naturally oriented path should be, but in this formula, the only restriction we have is on the orientation, right? It's naturally oriented. We don't have any restriction on where the non-trivial weights should appear. So that's why we talk about this set S. So in the computations we've done, we saw that whenever you have two successive non-trivial weights, like let's say if you have a non-trivial weight at vertex 2 and vertex 4, they cannot both contribute to regularity. Like you have to compare the contribution of each of them. So we'll see this in the next example. So that's why when I look at subsequences of my weight sequence, I want to pick the ones that satisfy this distance to away condition. So in your subsequence, if you're looking at the distance between two successive things, you don't want it to be 2, okay? And then regularity is the maximum. So maximum is taking over all these subsequences from our set S. Remember, these are distance, like the subsequences which satisfy distance to away condition, right? So what you see here is, this was our notation for the weight position sum, right? And the next thing you see is, so QT here is the last position, right? Q1 here is the first position. So in a way, when you look at the regularity, you're looking at these sums, which actually looks at all the weights, differences between all the weights, and you look at the distance between the last vertex and the last vertex of your path. So this is similar to what we saw in one non-trivial weight case. And in this one, Q1 was the first position, right? So you look at its contribution. That position matters a lot in the regularity formula too. And then we subtract t because we had t many non-trivial weight positions in that subsequences. So this is a very complicated process, right? Coming up with this formula was not really easy because you have to keep track of like what is changing the regularity. And then like taking this maximum, it was really hard to take the maximum and obtain this formula because you're comparing all these like subsequences of your weight sequence, and like maximum one has to contribute to, has to determine the regularity. Okay, so in a way, we generalize it and you can see the similarities between the formula for one non-trivial weight and any number of non-trivial weights. But this gets really complicated. So you have to compute these values. You don't know how many subsequences, appropriate subsequences you will need, right? Okay. So let's do this example. This formula you see here is the formula we claim. Actually, it's not the regularity, But this is the expression that will be used to compute the regularity. We're going to look at the maximums of these expressions for each subsequence, okay? Okay, so in the next part, let's think about this path, okay? So it's a path on 8 vertices. And what is its weight sequence? So weight sequence is the positions of non-trivial weights. So you have non-trivial weight at 2, so you have 2. Non-trivial weight at 4, so you have 4. Non-trivial weight at x5, non-trivial weight at x8. So this is our weight sequence. If you remember, I introduced this set S. And it was the subsequences of this weight sequence which were distance 2 away. So if you see 2 and 4 are distance 2 away. So if I'm looking at the maximal element of this set S, when I say maximal element, I'm talking about the length of that subsequence, right? So I cannot take 2 and 4 at the same time. So I have to make a choice. So I will look at 2, 5, 8 or 4, 5, 8. Okay? So and then if you compute the value of your function f at that weight sequence, you get 10. And if you compute it for the other maximal element, you get 7. So the maximum one wins the game and it becomes the regularity, right? So 10 is the regularity. So let's look at this other example. We still have a path on 8 vertices, and this time our weight sequence is 2, 4, 6. So if you see, we have all the non-trivial weight positions are like all the successive ones are distance 2 away from each other, right? So the things you can choose as maximal elements of S are, so maybe you're going to take away 4. So you can take 2 and 6, but you cannot include 8 there, right? Because if you include 6, 8 cannot be part of that maximal element in S. Okay, so you can take 2, 6, or you could take 2, 8, right? And the other one is, if you're moving 2, the only option you have is 4, 8. So for this weight sequence, the maximal elements you can choose from your set S are these subsequences. So for each of them, if you compute this value of this function, you get 7, 8, and 5, and the maximum value wins. Right, okay, so I have more to say, but maybe a good closing point will be to talk about the equivalent of this theorem for cycles. And I will stop here, even though I would like to talk about the other part. So maybe I'll give another talk when you run out of speakers. Okay, so in the last result, we're going to express the regularity formula for the cycle. So we have the same structure, but in a cycle, you close back here, right? So if you were working with a non-trivial weight here and non-trivial weight here, you also care about the distance between Q1 and Qt, right? So we have this additional condition that your first and the last thing you chose in the subsequence has to be distance 2 away too. Because you're closing your circle, besides this weight position sum, you will look at the distance between and your first component, your last non-trivial weight at the same time. In a path, you were looking at n minus qt over 3, q1 plus 1 over 3, right? But on a cycle, all these things are connecting back to each other. So you look at this ratio and the floor of that. Okay, so I'm going to stop here and see if you have any questions.
Thank you very much. Let's react to Selvi in the chat.
And while you're reacting, I'm going to show you my last slide. You might think this is an ugly animal, but it's one of the most beautiful animals. It's a tardigrade if you don't know it. So I think they're very cute and ugly at the same time. And I want to close my talk with this slide.
Thank you very much. If you ask me what this was when I was maybe 5 years younger, I would ask you, is this a Syzygy?
Ooh, I'll name this one Syzygy. Okay.
Any questions?
Can I ask a question?
Yeah.
I'm sorry if it is obvious here, but how you find the maximal element in the sequence? I don't understand.
So let's see. Yeah, this is a very tricky detection, actually. So this is our weight sequence, right? That part is probably clear, right? We're just looking at the positions. So for the maximal elements, we're looking at subsequences of this, which are not distance to a weight. Like whenever you're picking something, a subsequence. So let's see if we could choose 2, 4, 8. I cannot choose this one because 2 and 4 are distance 2 away, right? The distance between 2 and 4 is 2. So I cannot do 2, 4. So I can do 2, 8, right? Then if I could, I would see if I could do 2, 4, 6. Well, I cannot do 2, 4 at the same time because 4 is obviously like 2 after. So I know I cannot pick that one. So you're doing these, like you maybe fix your first non-trivial position and see what you can, like what choice you can make in the next step. And then once you make that choice, you look at what choice you can make for the next component and so on. So does this help?
Okay, yeah, thank you.
Yeah, of course.
Any other questions or comments?
Can I ask one question?
Sure.
Thank you, Selvi, for the talk. It was very nice. You have a restriction on these subsequences. You said it should be different from 2, right?
Mm-hmm.
And if you look at the starting point, your talk, what is the meaning of this restriction in terms of the language of this resolution?
Yeah, great question. So we don't really know what it means, right? Like this is a very small step towards understanding what kind of operations, like what happens in this is when we have an edge ideal for a weighted oriented graph. So when you change the exponent of one of the variables in your generator, like how does it change the minimal Fourier resolution? That's what we're trying to see. But there is not a regular pattern here. Like, it's like, I cannot really relate it back to minimal Fourier resolution immediately and how I cannot say how it will affect it. But I know that whenever I have degree, like distance 2, I know the winning generator will come from comparing the generators, like relations between the relations when you look at like the second vertex and the fifth vertex, maybe. Like, I don't know if this helps. We don't have the complete understanding, so I cannot really give you a clear answer on that. But my hope is when you look at those relations, it kind of tells you maybe which ones you're picking. Like you have all these relations, but the one that will play a role in the minimal Fourier resolution will come from looking at this piece and this piece.
I see. Okay, thank you.
Is there a toy example for which these ideas work?
For minimal Fourier resolutions, I don't have a toy example because this is like, we're not really relating with this with the Betti numbers even, right? What I tell here is like, oh, the shifts and the position will be like 8 in this example, right? So the width of my minimal Fourier resolution will be 8, but I can't really tell you which step and which syzygy I'm looking at. I don't, like, it's a mystery. I don't really know which Betti number gives me this.
Mm-hmm. Can I also ask a question which is not exactly related to your theorem, but to the very beginnings of the talk? So these edge ideals, even without any weights, when you have weights, do they have anything to do with representation theory of quivers?
People say that there is some relation, but I don't really know much. Like I went to some quiver talks and I was like, oh, there are these digraphs.
I mean, yeah, they
but I don't really know much.
Okay. Yeah, actually, Emine, are you here? Yes, she's here. We have been trying to create questions to ask you lately. We are meeting with her every week, and we will ask you some questions about this more.
Yeah, and that would make me very happy.
Okay.
But I don't know much about how this would be used in representation theory. Maybe the objects are similar, but the processes we look for are different. Or
Yes.
maybe there's an overlap. I don't know it really well.
Okay. And one more small question. You said that you cannot use any Stanley Reisner, that's the name, for the
Correspondence, yeah.
questions if you have weights. Are there any people who are trying to get some other sort of topological correspondence for weighted oriented
I
graph?
think, yeah, so that was my first thing actually. So I couldn't get to the later part of the talk, but that was what I was trying to do. So maybe I cannot, like right now, we don't have one simplicial complex that describes everything about your ideal. So far, what we have is that upper causal simplicial complex, but you have to look at that special multi-degree, right? Like it doesn't completely describe the weighted oriented graph. So there isn't a like general simplicial complex that we can use, and it would be really nice to come up with one. And I'm thinking about it, but so far no success.
Okay, thank you. Let's thank you again if there are no more questions. Clap.
Okay.
Then that is it for today. We are going to have some chat, which is unrecorded, the record. Then next week we are going to meet again with Enis, who just had to leave. I see in chat, and he's going to talk about some number theory, explicit Vologodsky integration for hyperelliptic curves. So see you next week. And if you want to hang out for the tea time after this, you can just stay here. Bye bye.
Okay. Thank you, Selvi. Bye bye.
Okay, thank you.